And this is going to be Chapter 5, the Electrocardiogram, Understanding EKGs. The objectives here, define the term electrocardiogram, describe the basics of EKG monitoring, list the types of EKG leads, discuss the relevance of Einthoven's triangle, identify and explain the grids and markings on a representative strip of EKG Graph Paper, describe the relationships of the following EKG waveforms to the electrical events in the heart: the P wave, the PR interval, the QRS complex, the ST segment, and the T wave. The electrocardiogram. Electrocardiogram is a graphic representation of electrical activity of the heart. The electrocardiograph, machine used to record the electrocardiogram or EKG machine. And an EKG, graphic tracing of electrical activity of the heart, not mechanical activity. So the electrocardiogram is a graphic representation on the activity of the heart, and this would be, if we run a 12 lead or did a strip, this would be the actual strip, an electrocardiogram or an ECG. The electrocardiograph is a machine, so this is the actual LifePak 12 or LifePak 15. EKG, graph tracing of electrical activity of the heart, not mechanical activity. So the EKG is going to show the electrical activity only, but we could also be pulseless in this. One of the rhythms that we're going to learn in ACLS is called pulseless electrical activity, or PEA. So this does not show the mechanical activity, this does not show the cardiac output, it only shows the electrical activity in the heart. The electrical basis of the EKG. Electrical activity is sensed by the electrodes placed on the surface of the skin, and we generally place 4 of them, recorded in the form of an electrocardiogram. Cardiac monitor depicts electrical impulses on the monitor scene or oscilloscope. Now, whenever we're looking at the EKG, everything that is above, this is called the isoelectric line, everything that is above the isoelectric line means that the electricity was headed towards a positive electrode, and everything below the isoelectric line means the electricity was headed towards a negative electrode. Now, this is going to become important whenever we're looking at 12 lead later on in the EKG. The electrical impulses present on the skin surface are very low voltage. Impulses are amplified by the EKG machine. A printed record of the electrical activity of the heart is called a rhythm strip or an EKG strip. EKG leads. Electrode. An electrode is an adhesive pad that contains conductive gel and attaches to the patient's skin. And then leads. How electrodes are connected to the cardiac monitor. 3 leads must have a positive, a negative, and a ground. The bipolar leads have 1 positive and 1 negative. That's why they're called bipolar. They have 2 poles. The limb leads. Lead 1, left arm and right arm. The left arm is positive and the right arm is negative. In lead 2, left arm is positive and the right arm is negative. Lead 2 is most common due to its ability to visualize the P wave. It also looks at the normal way that the electricity should travel at the heart. So we get our best look at the electricity traveling through the heart, if it's headed in the right direction, by looking at lead 2. And then lead 3. Left leg is a positive electrode and the left arm is a negative electrode. And so whenever we're looking at this, we put a electrode here, 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 and here on most LifePak 12 or LifePak 15 models. The positive electrode, this is lead 1 here. This is lead 2. And then this right here, this cross-lateral, is lead 3. Positive electrode in lead 1 is here. Positive electrode in lead 2 is here. Positive electrode in lead 3 is here. Leads 1, 2, and 3. When looking at the waves, the P wave identifies atrial depolarization. The QRS identifies ventricular depolarization. The T wave is the actual repolarization of the ventricles. The atria probably repolarized well, but it's hidden somewhere probably in the QRS. EKG leads. Information obtained from the EKG strip analysis. Whenever looking at the heart rate, is the rhythm regular? And yes, you can get that from an EKG strip. You can get the actual heart rate as well. Impulses, conductions, and time intervals, you can get that as well from looking at the EKG strip. Abnormal conduction pathways, and that is also a yes. Pumping action, you cannot get that information from an EKG. Cardiac output, again, you cannot get that action from the EKG. The blood pressure, or the formed cardiac output, or the hemodynamics of the person. And the answer is no, you cannot get that from the EKG. Cardiac muscle hypertrophy, and no, you cannot get that from a basic EKG as well. So all the lower end here is no, no, no. And for all the top, the answer is yes, what you can get from an EKG strip. And that would be heart rate, regularity, time intervals, and conduction pathways. Placement of the bipolar leads. Lead 1, positive electrode needs to go on the left arm, and the negative electrode needs to go on the right arm. For lead 2, the positive electrode needs to go on the left leg, and the negative electrode needs to go on the right arm. For lead 3, the positive electrode needs to go on the left leg, and the negative electrode needs to go on the left arm. Again, what I drew earlier, and this is Einthoven's triangle, which is an imaginary inverted triangle formed around the heart by the proper placement of bipolar leads. Top formed by lead 1, right side formed by lead 3, and the left side formed by lead 2. Each lead represents a different look or view at the heart, and that's always going to be from the perspective of the positive electrode. So this here is lead 1, this here is lead 2, and this here is lead 3. Positive electrode, positive electrode, positive electrode. Einthoven's triangle. We are going to assign degrees to this. So this plane here that we're looking at first, or lead 1, is going to be the first plane that we look at. And it's going to be our starting point because we're going to find the direction of the electricity in the heart from known points. And these are our known points. So all of our leads and our augmented voltage leads, those are all known points. So let's start off with lead 1 here. The positive electrode on lead 1 is at 0 degrees. Lead 2, from this electrode to this electrode, is approximately 60 degrees, which is this plane right here. Positive 60 degrees. Lead 3, which goes from this electrode here to this electrode here, is positive 120 degrees. Now, all of these that I'm fixing to circle here, AVR, AVL, and AVF, are the augmented voltage leads. So how the computer figures those is after all three bipolar leads are present, it actually puts a center ground where all of the lines intersect. And from that, we'll look at entire regions. An example of this, whenever it's looking at augmented voltage left, it changes the polarity of things to where it's looking from this direction and this perspective. When we're looking at augmented voltage right, again, we're looking from the negative 150 degree camera shot or this perspective here. When we're looking at augmented voltage front, we are looking at the heart and the electrical movement from this perspective here. So these are 6 known points. And those 6 known points are displayed and called Einthoven's triangle. Now the triangular representation is still there, but it is an inverted triangle, if everyone will remember. The EKG paper leaves the machine constant speed of 25 millimeters per second. Time measured in a horizontal line. We only actually measure two things on the EKG paper. We measure time and we measure amplitude. Amplitude or voltage measured on a vertical line or graph paper. Now each one of the smallest boxes on here, or this little box, is represented here in this bigger picture. Each one of those is worth 0.04 seconds. That means that 5 of them, 1, 2, 3, 4, 5, is equal to 0.20 seconds. As far as amplitude goes, up and down, we just talked about that. Let's go ahead and go through this. We'll talk about amplitude here in just a second. Okay, so the paper is divided into small squares, and these are the smallest squares that are on there, which are worth 0.04 seconds. There's 5 of them in a large box. This area here is a large box. 1 millimeter in width is equal to time interval of 0.04 seconds. Darker lines divide the paper into fifth square, vertically and horizontally. Large squares measure 5 millimeters of height and width. Represents time intervals of 0.20 seconds. 5 small boxes in each large square. Wave or wave movement refers to the movement away from the baseline or isoelectric line, beginning and ending of all waves, which is this right here. This is the isoelectric line. So this is going to be our standard here of what 0 amplitude is, or 0 degrees. A positive deflection, meaning that it's headed towards a positive electrode, is anything that is above the isoelectric line. A negative deflection, or negative, would be below the isoelectric line. So all of these waves that we see down here, this is a negative deflection, this is a negative deflection, but all the ones that we see on the top there, the P, the R wave, and the T wave, are all above the isoelectric line or positively deflected. An electrical impulse leaves the sinoatrial node and produces a waveform on the graph paper. Once completed, the cardiac cycles equals P, QRS complex, and T wave. And let's draw a heart here really quick and show you the relation of this. This is a review from the previous chapters. The electricity starts, or the stimulus starts, in the sinoatrial node. It travels across the interatrial pathways, simultaneously contracting the atria. The wave hits the AV node, which sends it down the left and right bundle branches. The P wave starts, and it is above the isoelectric line because it hopefully started in the sinoatrial node and is headed towards a positive electrode. And just so that you all can see this, I'm going to draw lead 2 up here, which is at 60 degrees. The negative electrode is here on lead 2. So the actual electricity, let me change colors here so it's easier to see. And this is going to be a dark blue. The wave starts here and heads in this direction. And since it is headed towards a positive electrode, the P wave is upright or above the isoelectric line. The Q wave, just for a split second here at the AV node, we can see it actually turn into the left and right bundle branches at the His-Purkinje level. This turning looks like it's turning away from a positive electrode, or swooping just a little bit to the negative. After that point, it gets back on track and heads towards the apex. This spot in time and this spot in time are the same one. As it turns negative, this is the electricity traveling back towards the negative electrode, The repolarization occurs here and hopefully is in the same direction, which is this way, as our depolarization wave or our contraction. The P wave. And I'm going to draw a lead 2 on all of these things here so that we can see negative, positive electrode. The P wave is upright because it starts at the SA node and it is headed in this direction. First wave produced by an electrical impulse from the SA node. Smooth, rounded upward deflection. Depolarization of the left and right atria should last somewhere around 0.10 seconds in length. The P wave is upright because it is headed towards a positive electrode. The PR interval. Time impulse travels from the sinoatrial node through the internodal pathways in the atria towards the ventricles. So it starts here and is traveling in this direction, but the PR interval is the time that it takes for it to depolarize the entire atria and make it to the AV node. The time interval from start of the P wave to the start of the QRS is 0.12 to 0.20 seconds in length. This is a very important number to remember. The PR interval should be no greater than 0.20 seconds. The QRS complex consists of the Q, the R, and the S waves. Represents the conduction of impulses from the bundle of His through the ventricular muscle, and this would be the ventricular depolarization. Again, the QRS complex is here on the EKG paper. The SA node has already fired. There's our P wave. It goes across the atria. It travels to the AV node. At the AV node, I get transmitted into the bundle of His and continue to travel in this direction. The R wave, and this point right here at the apex is about the same spot. It then turns into the ventricular muscle, the bundle branches, in the Purkinje system, and we get a movement away from our positive electrode at 60 degrees in lead 2. At that point, it's turning back towards the negative electrode. That's why we get a negative dip here. This right here at the end of the S wave is the return to the isoelectric line, and this is the loss of electricity in the ventricles. The Q wave is considered the first downward deflection. This is the Q wave. The R wave is the first upward deflection, the largest deflection seen in leads 1 and 2, and this is the R wave right here. The S wave, downward deflection after the R wave, and this is the apex of the S wave. So this is together, this is the QRS. Measures less than 0.12 seconds, or 0.12 seconds, or 3 small boxes. This also is an important number. If it is greater than 0.12, we are going to consider that to be a possible ventricular rhythm. It's outside the pathways. It took a lot longer. Now it's being conducted through the muscle tissue itself. So the QRS interval should be no greater than 0.12. ST segment, a time interval during which ventricles depolarize and repolarization of the ventricles begin. The isoelectric line or consistent with the baseline. So everything that is not an actual waveform in this is the isoelectric line. And the ST segment is this spot right here between the S wave and the T wave. This spot here, not shown on this slide set, but we will talk about it at a later point, is called the J point, which is the spot that the S wave should have returned to the isoelectric line. The T wave follows the ST segment, represents ventricular repolarization. So after this depolarizes, or the electricity moves through it, this entire section needs to get ready to do this all over again. It's slightly rounded, positive deflection. Resting phase of the cardiac cycle is what the T wave is, or repolarization of the ventricles. Summary of EKG waveforms. The P wave identifies atrial depolarization. The QRS identifies ventricular depolarization. The T wave identifies ventricular repolarization. This is the ST segment, and where the S wave should have returned to the isoelectric line is also considered the J point. That's going to conclude Chapter 5, the EKG.